Under a wide, quiet sky, we sit with the slow glow of distant starlight, and the long path that light has taken already tells us something. Space moves at its own pace. On Earth, our clocks feel steady, yet out there, their rhythm can bend with speed and gravity. So a clock near a heavy pull may run a little slower, and one moving very fast may tick a little differently. From these simple ideas comes a careful question we'll explore tonight. Could time be traveled, not just counted? We'll take it step by step, using clear language and gentle examples, and leave the heavy math at the door. If Calm Space Guides help you relax and learn, please like and subscribe. It truly helps. Settle in, breathe easy, and let's begin. Time is not something you can hold, yet it shapes every part of life, setting the order of mornings and nights, guiding plans, and leaving its mark on memory. Clocks and calendars give us neat numbers, but those numbers are only tools. They help us keep track, while time itself is the thing being tracked. Thinking that the readout is the reality is like thinking a thermometer is the same as heat. The deeper story is quieter and more complex, and it reaches into how the universe is built. A clear way forward is to ask what time really is, then look at what modern science says about moving through it. Moving very fast or living near strong gravity can shift how quickly your time passes, compared with someone else far away and at rest, which is not a trick, but a measured effect. In that sense, stepping into the future faster than others is real, even if doing it at a human scale is hard. The past raises harder questions. A wormhole, explained simply as a tunnel-like shortcut through space and time, could, on paper, link two moments. But keeping such a tunnel open would require unusual forms of energy, and even if that hurdle was solved, the path would invite paradoxes where causes and effects collide. When ideas reach those edges, they meet the limits of today's theories, where our models become uncertain and familiar rules strain. The goal is not a dramatic promise, but a careful test. What would a working design have to satisfy? And what do our best measurements allow? Daily life makes time feel straightforward. It runs in one direction. It moves steadily enough to set routines and to count years. You wake, you eat, you work, you rest, and you can point to a watch or a calendar and say when each happened. This picture is useful because it matches most of experience and keeps society coordinated. Yet usefulness is not the same as completeness. The more closely scientists measured time and motion, the more they found that time is tied to space in a deep way, and that its rate depends on conditions. The modern view brings space and time together into one connected framework called space-time. This word is not a flourish. It means that where and when belong to one structure, so that you can only give a full description of an event by naming both together. Three directions describe position. One direction orders events. Taken as a whole, they form a four-dimensional map that sets the stage for everything that happens. It is natural to think of space as distance left, right, up, down, near, far, and time as order before, during, after. But in the universe, they do not stand alone. Changing your state of motion changes how your time runs. Changing the gravity around you changes how your distances and durations relate. This linking is not just a new way to speak. It was tested in many ways across the last century, from beams of particles that live longer when they move fast, to clocks flown on planes and satellites that need tiny corrections to stay in step with clocks on the ground. The point is steady. Time does not tick the same for everyone, everywhere. It keeps a local rhythm set by speed and gravity. Before the 20th century, most scientists treated space and time as fixed and separate. Time was assumed to pass at one universal rate, the same in every setting. Space was taken as a rigid stage on which things move. That view solved many problems, yet it did not fit all the evidence. Albert Einstein changed the picture by showing that space and time are flexible. In special relativity, and then in general relativity, he proposed that space-time can stretch, bend, and even ripple, and that matter and energy tell space-time how to shape itself, while space-time tells matter and energy how to move. This is where gravity takes on a new meaning. Instead of a pull acting across emptiness, gravity is the geometry of space-time around mass and energy. A star, a planet, or any heavy object makes a kind of dent in this geometry, and nearby objects follow paths that curve because the space and time they move through are curved. A simple image helps to hold this idea without turning it into a story. Picture a flexible sheet held flat, and then imagine placing a heavy weight on it. The sheet dips around the weight. If you roll a small ball across the sheet, its path bends toward the dip, not because a string pulls it, but because the surface it rolls on is not flat. In the same way, planets orbit stars because they follow the natural paths set by the shape of space-time near the star. This image is only a guide, since the real effect is four-dimensional and involves time as well as space, but it gives a clean sense of how shape can guide motion. The important part is that nothing reaches out to tug. Objects move along the straightest possible routes allowed by the curved geometry, and those routes look curved when you draw them on a flat page. Because space and time are joined, any bending that affects distances also affects durations. Near a large mass, time runs a little slower compared with far away. The difference is tiny near Earth's surface, but measurable with precise instruments. Near very strong gravity, like that around a neutron star, or near the edge of a black hole, the slowing becomes large. Motion plays a similar role. When you move very fast compared with someone else, your time stretches so that less time passes for you between two meetings than for the person who stayed at rest. This is the core of time dilation. It has been confirmed by timing fast-moving particles that survive longer than they would at rest, and by adjusting satellite clocks so navigation systems stay accurate. These are not side cases. They are part of the routine care needed to make high-precision technology work. Hearing that time slows down can sound like a play on words, so it helps to phrase it carefully. Each person or device traces a path through space-time, and along that path, a clock will record a certain amount of elapsed time. The amount depends on the path. Two paths that start and end at the same events can include different amounts of time between those events. That is why one traveler can age less than another without breaking any rule. What changes is not the essence of time, but the route taken. Speed and gravity set the route, and the route sets the tally. From this, the idea of traveling to the future follows without drama. Spend time moving fast or waiting near strong gravity, and then return to people who stayed in weaker gravity and moved slowly, and you will find that more of their time has passed than yours. You have stepped into their future by using the way time depends on conditions. The barrier is practical. Reaching the necessary speeds with human passengers and keeping them safe, or sitting near intense gravity without harm, is hard. Energy, shielding, and engineering limits all press back. Still, the effect itself is part of physics, not fiction. Turning toward the past brings in open questions. A wormhole can be described in simple terms as a tunnel that links two distant regions of space-time. If such a tunnel could exist, be held open, and be controlled, and if one mouth were moved in a way that changes its time relative to the other, then the tunnel might connect two different moments. This chain of ifs is long. Known physics suggests that holding a wormhole open would call for matter or fields with negative effective energy density, which is not something we can produce and sustain at large scales. Even if that obstacle were solved, the path could create paradoxes, where an action prevents the past conditions that made the action possible in the first place. Some ideas try to avoid the clash by requiring that all events be self-consistent or by allowing separate branches of outcomes, but none of these approaches has firm experimental support. They are ongoing proposals, not settled facts. As we push farther, we meet places where our current theories give unclear answers, near the core of a black hole, or when we try to describe the very first instance of the universe. The math points to behavior that our present models cannot handle well, with quantities that grow without bound or with rules that stop working. Many researchers think that a full theory that joins gravity with quantum physics, the framework that explains atoms and light, will be needed to clear up those points. Until then, any design for a device that loops time backward remains a study in conditions and limits, not a blueprint for construction. Working through those limits is still useful because it shows which features of space-time are robust and which are not. In Einstein's relativity, the math does not mark events as past, present, or future. Those labels come from our experience, not from the equations. The theory describes how time behaves along with space, how both can stretch, bend, and link together without pointing to any special slice called now. Time is treated as a dimension that stands beside the three dimensions of space. To locate an event, you give 3 numbers for position and 1 number for time, and the 4 together tell you where and when the event sits in the universe. Space feels open in every direction, while time in daily life feels strict. We live in one moment and then the next, never the other way around. Yet in the mathematical picture, all moments are simply part of the same structure. The theory lays out the entire space-time block at once and does not pick a favorite moment. From this comes a careful idea. Time might not flow so much as be. Just as places all exist whether or not you stand in them, moments could all exist whether or not you are currently in one of them. The flow we sense could be a feature of how minds track change, not a part of the laws themselves. That does not make time unreal. It says that the feeling of its motion may not come from gravity or geometry. Still, our world shows a strong one-way pattern. We remember the past, not the future. A dropped cup breaks and does not leap back together. A match burns down and does not rebuild itself from ash. Bodies age and do not run that process in reverse. If the deep equations do not choose a direction, something else must set it. To find that source, scientists look to thermodynamics, the study of heat and energy, and especially to a rule called the second law. In a closed system, one that does not exchange matter or energy with its surroundings, entropy tends to increase. Entropy is a measure of how many ways the parts of a system can be arranged without changing what you see at the large scale. More ways means more disorder. The egg on the kitchen floor is a clean example. When the shell is whole, there are far fewer microscopic arrangements than when it is shattered and the yolk is spread. The broken state can be arranged in more tiny patterns, so it has higher entropy. The path from whole to broken is likely. The path from broken to whole is so unlikely that you will not see it happen on its own. The same logic shows up everywhere. Ice melts, because the warmed, jumbled state is accessible in more microscopic ways than the crisp crystal. Stars burn their fuel and drift toward cooler, simpler end states. Even the expanding universe converts earlier, tighter arrangements into later, more spread out ones. The rise of entropy provides a natural direction from before to after. It gives time an arrow, even when gravity and motion stay neutral about direction. You can see this arrow in a simple film. Play a video of a glass falling and smashing. Now, play it backward. The reversed version is easy to spot, not just because it looks unusual, but because it violates the trend toward higher entropy. The tiny details that would be required for shards to leap and join exactly are so special and rare that they will not occur by chance. This is why you can look at a short clip and tell which way time is running. Your brain is reading the entropy pattern and calling out the natural direction. There is a subtle point here. Many of the basic laws of physics are time-symmetric, which means they work the same if you flip the direction of time in the equation. They do not forbid the unbreaking of the glass. They simply do not favor it either. What picks the forward direction in practice is the arrangement of matter and energy and the steady push of entropy. Direction comes from statistics, not a built-in arrow in the core rules. When you scale up to the size of daily life, to the size of stars and galaxies, the statistics become overwhelming, so the one-way character feels absolute. If time in the equations does not single out now, it raises questions about memory and prediction. We can store records of what has already happened, but we cannot pull detailed records from what has not yet happened. The reason lines up with entropy. Records, like photos, tracks, and scars, are stable imprints. They form when a system moves from a low entropy state to a higher entropy one, while leaving a mark. Making a reliable record in reverse would require arranging countless parts in exactly the right way, which is not what nature tends to do unassisted. Our sense of past and future grows from the ease of making records in one direction and the difficulty in the other. This view also fits with clocks. A clock is a device that changes in a regular way, so we can count intervals. Every tick is a small, directed process that turns stored order into a slightly more disordered state, while keeping the motion repeatable. The direction of the count mirrors the direction set by entropy. On the smallest scales, a single event can go either way. On larger scales, with many parts interacting, the forward direction dominates because there are many more ways to be disordered than ordered. Space-time and entropy, taken together, give a stable picture. The geometry of space-time does not pick a preferred moment. It sets the paths and rates that clocks will follow, depending on speed and gravity. Thermodynamics adds the direction we feel by showing why processes favor one side of time over the other. The two ideas do not cancel each other. They sit side by side. One tells you there is no universal now. The other tells you why eggs break and do not reassemble, why heat spreads, and why smoke does not gather back into a match. There is a practical side. If all moments sit in the space-time picture and the arrow comes from entropy, the present may not be as unique as it seems. The future is not produced from nothing. It is a region that systems approach as they follow their most likely paths. The past is not gone in the math. It is a region those paths came from. None of this lets you step freely among moments. It only reframes what before and after mean when you look with the tools of physics. Movement through time still depends on the path you take, which is set by speed and gravity. Direction still depends on how many arrangements are possible and on how systems naturally drift towards states with more options. When people ask whether time could run backward, the best answer is careful. The basic equations do not forbid a reverse run. Yet the conditions needed to make it happen for a complex system are so exacting that nature will not arrange them on its own. If you reduced a system to just a few particles, you could script a reverse path, but adding real-world complexity would break that script almost at once. A single stray interaction would spoil the perfect choreography that a rewind needs. That is why reversing time for ordinary objects is not seen, and why thermodynamics keeps its hold. The same care applies when we ask about travel through time. The space-time model allows different rates of time to be experienced along different paths, which is why going fast or staying near heavy masses can move you into a later date compared with someone who stayed put. That part fits the rules we have tested. Moving into the past faces the entropy problem, as well as the geometric and energy barriers already discussed. Even if a path in the geometry could be drawn, keeping processes consistent with the one-way march of disorder would be a major hurdle. Proposals that try to avoid contradictions often end up changing the story so that no real violation of the arrow takes place. All of these points connect smoothly with what came before. Time does not tick the same for everyone, because motion and gravity change the rate along each path. The equations of relativity do not pick out a present, so the feeling of now does not come from geometry. The direction we live with comes from thermodynamics, which favors the spread from order to disorder. Together, these ideas explain why we can age at different rates without breaking rules, why broken things do not fix themselves, and why the idea of stepping backward in time runs into both logical and physical walls. Relativity does not choose a special now, and the arrow we feel comes from entropy, yet rates of time still differ along different paths. A clear human example is the long career of Russian cosmonaut Sergei Krikalev. Over nearly 2 decades, he flew 6 missions and spent about 803 days in orbit, more than 2 full years living and working above Earth. He first launched on Soyuz TM-7, inches 1,988 to the Mir station, returned to Mir multiple times, and later joined joint missions with NASA as spaceflight shifted from rivalry to cooperation. In 1991, he orbited through a rare moment in history when the Soviet Union dissolved while he was still aloft. And then in 2000, he served on the first long-duration crew of the International Space Station. A 6th flight in 2005 pushed his total above 800 days, which was a world record at that time. Life on those missions meant months at a time in microgravity, floating, repairing hardware, running experiments, watching day and night sweep by every 90 minutes. It also meant riding at orbital speed, roughly 7.66 kilometers per second, about 28,000 kilometers per hour. At that speed, special relativity comes into play. The rule is simple to state. Compared with someone at rest on the ground, a moving clock ticks a bit slower. Clock here includes the human body, since every process in cells follows the same physics. The effect is small at ordinary speeds and grows as speed rises, so for most of us, it is invisible. In orbit, it becomes measurable. Across Krikalev's total time aloft, the slowdown added up to around 20 milliseconds. That is a sliver of a second, yet it is a real difference. If he had stayed on Earth, his tally of elapsed time would have been about 20 milliseconds greater. Having flown instead, he aged that much less. This is not a trick of language. It shows up whenever we compare precise clocks that take different paths through space-time. Identical atomic clocks are the usual tools. Leave one on Earth and send the other along a fast route. Then bring them back together and compare. The traveler will read a tiny bit behind. In 1971, a well-known test by Joseph Hafele and Richard Keating flew atomic clocks on commercial airliners around the world. and found differences that matched the predictions. Modern navigation satellites also provide daily confirmation. Their clocks are adjusted because motion slows them, while weaker gravity at their altitude speeds them, and those two effects must be balanced to keep timing accurate. Without those corrections, positioning would drift. The idea can be written as a compact formula from special relativity, but it does not require heavy math to grasp. The time measured along a moving path depends on the speed v compared with the speed of light c. As v gets closer to c, the moving clock accumulates less time between the same two events. In symbols, you sometimes see tt equals t1v2 divided by c2, where t is the interval the traveler records and t is the interval for someone at rest. The square root in the denominator tells you the story. Push v higher and the denominator shrinks, so t stretches relative to te. In plain words, the traveler's time runs slow. Orbit adds a second, gentler ingredient from general relativity. Gravity also affects rates. Higher altitude means slightly weaker gravity than at Earth's surface, and weaker gravity lets clocks tick a bit faster. In low Earth orbit, the speed effect wins, so the net result is a slow clock and a slightly younger astronaut on return. Far above, as with GPS satellites, the altitude effect can outweigh the speed effect, so their clocks tend to run fast unless corrected. Either way, the need to account for both influences is a sign that space and time are joined and that rates are local, not universal. Thinking in everyday images helps. Picture two nearly identical journeys that start together and end together. One path stays at rest near Earth's surface. The other loops around the planet at high speed for a long while and then comes home. Both travelers meet again at the same place, shake hands, and compare notes. The one who took the fast loop has experienced a little less time. Nothing was broken. Each clock kept perfect time along its own path. The paths were simply different. Krikolev's flights are a scaled, human version of this comparison. During each orbit, his ship circled Earth every hour and a half, skimming above the atmosphere in a steady fall that never reached the ground because the surface curved away. Every circuit shaved a tiny amount from the time he would have lived through if he had remained on the ground. No one noticed moment by moment. Only careful bookkeeping and precise physics make the small total visible. Add the circuits across hundreds of days, and a measurable difference appears. This leads naturally to the question of what happens if speed becomes extreme. If a craft could cruise near the speed of light, say 99.9%, the same rule would act far more strongly. A traveler could experience 1 year on board, while decades pass for people who stayed on Earth. From the traveler's point of view, nothing strange occurs. The ship runs, the clock ticks, meals are eaten, and work is done. From Earth's point of view, the traveler returns far into their future. The effect has a familiar name in classrooms, the twin paradox. But there is no real paradox once you remember that the twins follow different paths with different accelerations and turnaround points. Proper time, the time recorded along each path, need not match. It is useful to separate what the math allows from what machines and bodies can endure. To reach a large fraction of light speed, you need extreme energy, strong and reliable engines, and shielding against radiation. You also need to manage acceleration gently enough to keep a crew healthy. None of that changes the physics of time dilation. It simply sets the engineering hurdles that stand between the current pace of spaceflight and any future voyage that would make years in the ship match decades at home. Low Earth orbit shows the effect at the level of milliseconds. Higher speeds would make it dramatic. The size of the difference does not change the core lesson. Time is local. Each person, each device, each particle carries a private clock that depends on its path through space-time. Comparing clocks requires bringing them together and reading them side by side, and when you do, you find that motion and gravity have left their marks. These marks are not guesses. They are built into our timing systems, checked by repeated experiments, and lived quietly by long-duration crews. A cosmonaut, like Krikalev, after hundreds of days aloft, lands with a clock and a body that have counted slightly fewer beats. The rest of us have moved a touch farther along the shared calendar. The picture also shows why we speak carefully about traveling to the future. It is not about jumping ahead in some absolute timeline. It is about following a path that accumulates less time than another path between the same start and end events. Orbit and high speed are two such paths. Sitting deep in a strong gravitational field is another, though it brings hazards of its own. In all cases, the comparison is made when paths rejoin. The difference is the quiet remainder of many tiny shifts added together. Real missions continue to measure and use these shifts. Space agencies compare ground clocks with clocks on board stations and satellites. Navigation networks update their timing every day so that maps on phones and ships stay true. Research flights carry clocks to test predictions over and over. The same principles help physicists build ever better timekeepers, which in turn can sense altitude changes of centimeters because gravity's pull changes the tick by a hair's breadth. These are steady applications of one idea. Time depends on motion and gravity, and careful comparisons reveal how much. Examples like Krikalev's are helpful because they link abstract rules to lived experience. They turn a line in a textbook into a small but real change in a person's age. They also set a scale for imagination. Milliseconds over years in orbit are within reach now. Larger gaps would need speeds and energies far beyond current craft. Between those ends lies a wide range of possibilities that can be studied with clocks, with satellites, and with the long, unhurried patience that precision work always demands. Speed changes the rate of time, but it is not the only lever. Gravity changes it too, and it does so by shaping space-time itself. In general relativity, gravity is not a pull that travels across empty space. It is the curve of space and time around mass and energy. The heavier the object, the stronger the curve. The nearer you are to that mass, the slower your clock will run compared with a clock farther away. This effect is called gravitational time dilation. It sounds abstract, yet it follows a simple idea. When space-time is bent, both distances and durations are altered, and clocks follow the local shape. A well-known way to picture the strength of this effect is through a scene from the film Interstellar. The crew visits a world that circles very close to a huge black hole. Near such an object, space-time is stretched to an extreme, so the rate of time on the planet is far slower than the rate on Earth. Hours for the crew line up with years for people at home. The contrast is dramatic because a black hole is an extreme mass in a small region, and the curve it creates is intense. The story is fiction, but the setup reflects real physics. Physicist Kip Thorne advised the film and used general relativity to anchor the picture. Near very strong gravity, the difference in time rates can be large. The closer you are to the mass, the slower your time will pass. Away from black holes, the same rule holds with gentler numbers. In the 1,970 seconds, researchers compared two atomic clocks placed at different heights. One stayed near sea level. The other went up a mountain, roughly 2,300 meters above the sea. After about 11 days, the two were brought together and checked. The higher clock had ticked slightly faster. The difference was only a few billionths of a second, yet it matched the prediction. Higher altitude means a slightly weaker gravitational field, which means less curvature and a faster local rate of time. The clock closer to Earth's mass, down near sea level, ran a little slower because the field is a bit stronger there. Today, similar comparisons are made with even better instruments. Some laboratory clocks are so precise that lifting one by a few dozen centimeters can change its tick at a level they can detect. Putting speed and gravity side by side gives a clear picture. Motion slows a clock. Weaker gravity speeds it up. Satellites carry both effects at once. A GPS satellite moves quickly, which tends to slow its onboard clock. It also flies high, where gravity is weaker, which tends to make its clock run faster. Engineers account for both, or else the system would drift and maps would fail. The fact that these tiny changes must be corrected every day is a quiet proof that time depends on path and place. The pull of gravity on time raises a natural question. Could we use space-time itself to cross huge distances or leap far into the future? This is where a bold idea enters the warp bubble. In 1994, Miguel Alcubierre worked within general relativity and wrote down a mathematical metric, which is a way of describing the shape of space-time that would allow a compact region to move faster than light relative to distant points without the ship inside breaking the light speed limit locally. The key is that the craft would not move through nearby space in the usual way. Instead, the space in front would contract and the space behind would expand. Inside the bubble, the ship would be at rest relative to its local space, so the crew would feel no push. The bubble itself would slide across the universe. This sounds like a trick, but it stays within the rules of general relativity. The speed limit applies to motion through space, not to the way space itself can stretch or shrink. We already accept that the universe expands. Distant galaxies can recede from us faster than light because the space between us grows. A warp bubble is a compact version of this idea, driven in a chosen direction instead of everywhere at once. If such a bubble could be created and steered, a trip that would take light thousands of years could be covered in a much shorter time as seen by outside observers. Inside, the crew's time would pass normally. They might age months or years while centuries flow by outside. A gentle way to hold this thought is to imagine two modes of travel. In one, you push through space, like a boat through water. In the other, you sit still on a patch of water that moves while carrying you along. In the Alcubierre design, the craft is not plowing through space. The patch of space-time around it is being reshaped to move. No crushing acceleration would be felt by the crew because their local space does not demand speed from them. Their clocks tick at the usual local rate. The change appears when you compare their time with the time of distant places that were left behind and then met again after the bubble glides. The catch arrives with the energy needed to shape space-time in such a directed way. Alcubierre's solution requires regions of negative energy density, often called exotic matter. Ordinary matter and energy curve space-time in a way we read as attractive gravity. Negative energy would curve it the other way, acting like repulsive gravity. Quantum theory allows small, temporary patches of negative energy in special setups, such as the Casimir effect between closely spaced metal plates, but those effects are tiny and fleeting. They do not give us a stockpile to build a bubble wall. A second challenge is the amount of negative energy the original model seemed to demand. Early estimates suggested energy on the scale of a planet or more. That put the concept far beyond any practical reach. Later, researchers explored modified shapes for the bubble to reduce the requirement. Harold Sonny White, working at NASA's Eagle Works, proposed adjustments to the geometry that, on paper, cut the energy budget dramatically, from something like a giant planet to something more like a large vehicle. These revisions do not make the drive possible with present tools, but they show that the details of the bubble's shape matter and that the theory has room for optimization. Beyond energy, stability is a deep issue. A bubble would need to form, hold its shape, and be guided, all without tearing or dumping harmful radiation onto the ship. Some studies suggest that quantum fields near the bubble's edge could build up intense energy. If the structure failed, that energy might be released in a dangerous burst. Other analyses look at how to start and stop the bubble safely and how to avoid trapping signals and matter at its boundary. None of these are minor concerns. They are central to whether the idea can be more than a formal exercise. Gravitational time dilation fits naturally into this discussion because a warp bubble is a way of arranging curved space-time on purpose. Near a black hole, nature does the curving and clocks slow. In a bubble, the design would be chosen so that the clocks inside remain comfortable while the outside world experiences a different rate and a different mapping of distances. If a crew sat in a bubble for a year of their own time and the outside world jumped ahead by centuries, they would return as travelers to a later age, not because their bodies ran slow from speed or gravity, but because their local space-time carried them across a giant gap in the global map. The comparison, as always, would be made when paths meet again and clocks are set side by side. Even without bubbles, gravity already lets us see the link between height and time wherever we can measure it. Astronauts on the International Space Station sit higher than we do, which would, by itself, make their clocks run a bit fast. They also move quickly, which makes their clocks run a bit slow. In low Earth orbit, the speed effect is larger, so the net is a slow clock. Farther out, where satellites move more slowly and gravity is much weaker, the altitude effect wins, so those clocks run fast. Our systems work only because we include both effects and keep correcting them. Ground networks compare signals, adjust offsets, and keep everything aligned every minute of every day. That steady practice is a quiet form of experimental physics on a planetary scale. Closer to home, the mountain and sea level test has been repeated in many forms. Rockets have carried clocks high above Earth and returned them to compare. Physicists place ultra-precise clocks in labs on different floors and watch them drift apart and come back together when moved. These clocks count the tiny beats of atoms and can sense changes in gravitational potential at the scale of a small step. The lesson is the same each time. Lift the clock and it ticks faster. Lower it and it ticks slower. The signal is tiny, but with modern tools, it is clear. The black hole example from film reaches for the other extreme because it highlights what strong curvature can do. A spinning black hole can allow orbits very near its boundary where both gravity and orbital speeds are extreme. Time for a traveler in such a tight path would run much slower than for someone far away. We do not need to match the movie's numbers to see the main point. In strong fields, rates can separate by large factors. That is not a loophole or a stunt. It is a core part of general relativity. If we collect these pieces, a path appears. Speed can slow time. Gravity can slow or speed time, depending on where you sit. Curving space-time on purpose could, in theory, let a region move in a way that gets around the usual distance limits, without asking local objects to break the light speed rule. Each piece uses the same language. Clocks follow the geometry, and comparisons are made when clocks meet again. The hurdles are not in the logic of the laws, but in the materials and energies needed to shape space-time at will. There is also a careful point about signals and cores. A warp bubble that moves faster than light relative to faraway points raises questions about how information travels and whether cause can stay ahead of effect. Many versions of the idea keep the crew safe from impossible signals by ensuring that nothing inside moves faster than light relative to its local space, and by arranging the bubble so that signals cannot outrun the boundary. These details sit at the edge of current understanding and are part of why the concept remains in the theoretical file. They are not afterthoughts. They are central tests any real design would have to pass. The link between gravity and time will keep showing up in simpler contexts as well. Large planets, dense stars, and the regions near compact objects all shift the beat of nearby clocks. Light climbing out of a gravitational well loses a bit of energy, which we see as a small redshift in its color. Signals sent from a lower altitude arrive slightly stretched at a higher one. These effects are tiny for Earth, but not for extreme objects. They are built into how astronomers interpret data from space and how missions plan close passes by massive bodies. Warp bubbles, by contrast, are not part of current mission plans. They remain a formal possibility inside general relativity that asks for ingredients we cannot yet provide. Negative energy appears in quantum theory in brief, small patches that we cannot harvest and shape at will. Stability under quantum fields is not solved. Guidance, startup, and shutdown are open problems. Work that looks for ways to lower the energy budget or soften the edge conditions is useful, but it does not replace the missing pieces. Gravitational time dilation, though, is no longer an idea seeking its first proof. It is measured on mountains, in rockets, and in orbit. It is used every day by the networks that run navigation and timing. It ties back to the simple statement that time is part of space-time, and that rates are local. The closer you are to strong gravity, the slower your time flows. The weaker the gravity, the faster it goes. That rule, joined with the effect of speed, sets the stage for every serious talk about travel through time and across large distances, whether the setting is a laboratory bench, a satellite path, or a speculative metric written down to test the limits of the theory. Speed and gravity already show how time can stretch or compress along different paths. Another proposal looks stranger on first pass, yet still comes from the same mathematics: the white hole. In the equations of general relativity, a black hole appears as a region from which nothing can escape once it crosses the boundary called the event horizon. If you flip the solution in time, you get a mirror image with the opposite behavior. Instead of a region you can fall into and not leave, you get a region you can never enter, because matter and light are always being pushed out. This time-reversed partner is what physicists call a white hole. No pulling in, only throwing out. The idea is not a fantasy pasted on top of the theory. It drops out of the same family of solutions that describe non-spinning black holes. In the full, extended map of those solutions, there is a quadrant that behaves like a white hole, a source of particles and radiation that forever ejects and never accepts. If such an object existed, crossing inward would be impossible because every possible path is directed outward. You would not dive into a white hole the way you can fall toward a black hole. You would be turned away by the way space-time is shaped there. This is where wormholes enter the picture. A wormhole is a bridge that links two distant regions of space-time. In the idealized diagrams drawn from the same equations, one mouth can look like a black hole and the other like a white hole. Fall into the former, exit from the latter. If the bridge could stay open and stable, a traveler might pass through and emerge somewhere else, or somewhen else, because time is part of the geometry too. Near the entrance, gravity and speed would both be extreme. Inside, the mapping between before and after can tilt sharply. On the exit side, a different slice of the universe's time may line up with your arrival. Measured against the place you started, you could land far in the future even if only minutes passed on your own clock. A simple picture holds the core. Enter a deeply curved region where your proper time, your own clock, barely ticks while the outside universe continues. Emerge where space-time aligns again, and you will compare your small tally with the large tally of years that have passed elsewhere. In that limited sense, a black hole to white hole tunnel would act like a one-way jump forward. It would not let you steer to an exact year by turning a dial. It would not promise a safe return. It would be a path that uses the geometry to change which later you meet when you come back into normal space. The obstacles are not subtle. Real black holes are not gentle. Tides, the difference in gravity between your head and your feet, can be strong enough to tear matter. The inner regions of a rotating black hole have more complicated structure and, on paper, can contain paths that avoid the central singularity. Yet most studies suggest that even tiny disturbances can make those paths break down. Add in actual matter and radiation, and the neat, clean tunnels in the diagrams become unstable. White holes also have a problem in the other direction. If they constantly eject light and particles, they should be easy to notice, yet no clear example has been found. By contrast, black holes have firm evidence. Telescopes have traced stars looping around a heavy, dark object at the center of our galaxy. Gravitational waves have been recorded from pairs of black holes merging. A global array of radio dishes has imaged the shadow and glowing ring around a supermassive black hole in galaxy M87. White holes have no such record. Some researchers have asked whether a few quick, bright flashes in the sky gamma-ray bursts could be linked to white holes dumping energy. The data fit better with known sources: the collapse of massive stars and the collision of neutron stars. Other work wonders whether the newborn universe could have produced tiny, short-lived white holes that faded long ago. These are careful speculations, not detections. Even if nature provides a white hole somewhere, reaching it and surviving the neighborhood is another layer of difficulty. The region around any compact object is filled with high-energy particles and intense radiation. Navigation would be uncertain. A wormhole would have to be held open against collapse, which, according to many analyses, demands matter with negative effective energy density. We do not know how to supply that. And if a passage did exist, and you committed to it, you would have little control over where and when you exit. The tunnel sets the mapping. The traveler only rides it. Because the white hole path is so uncertain, people sometimes look for a quieter way to move into the far future. One approach does not ask space-time to cooperate at all. It asks biology to stop. If you could slow or pause the processes in your body without destroying the structure that stores memory and identity, your own time would nearly stop while the outside world continues. That is the idea behind cryonics. The plan is simple to state. Cool a legally dead person to very low temperature, aim to prevent further decay, and store the body, or only the head, until future medicine can repair the damage and restart life. Current practice uses liquid nitrogen to reach about -196 degrees Celsius. Before deep cooling, technicians add cryoprotectant chemicals to reduce ice formation. The goal is vitrification, where tissues form a glass-like state with fewer sharp crystals. After preparation, patients are placed into insulated metal vessels and left in long-term storage. Some arrangements preserve the whole body. Others remove and store only the brain, reasoning that a future body might be rebuilt or replaced, while the detailed connections in the brain carry the information that makes a person who they are. The most famous early case is James Bedford, cooled in 1967 and still kept in storage today. Since then, a few hundred people have chosen the same path, with thousands more registered. The scientific hurdles are larger than the steel tanks that hold them. Cooling a human evenly and quickly enough to avoid injury is hard. Even with cryoprotectants, some ice can form, and crystals tear delicate structures. The chemicals themselves can be toxic or can cause stress when concentrations are high. Deeply cooled tissues can crack as they shrink. Rewarming is perhaps the hardest step. If the outside warms faster than the inside, gradients build up and damage grows. A future revival would need tools that can repair many kinds of small-scale injury while keeping the overall structure stable. It would also need ways to restart organs and restore function in a coordinated way. There are encouraging results at small scales. Single cells, simple tissues, and early-stage embryos can survive cooling and rewarming under controlled conditions. A few animal organs have been cooled and later recovered to partial function after careful warming. Though full success is not yet routine, these steps show that biology can, in some cases, be paused and resumed. Scaling that to the complexity of an adult human brain and body is a problem of a different size. It likely asks for advances in materials, in high-speed, uniform warming, in ways to block chemical toxicity, and in medical repair at the level of cells and the tiny connections between them. Because none of that exists today, cryonics is often described as a bet on future knowledge. It is not a medical procedure with a tested path back. It begins only after legal death, so by definition the person is beyond current recovery. This raises ethical and legal questions about consent, identity over long gaps of time, property and obligations during storage, and the rights of a revived person in a society that may have changed beyond recognition. It also raises practical questions. Who pays for the vessels and the nitrogen in a century? Who maintains the systems if a company fails? What counts as success if memories return patchy or altered? Set against those doubts is a plain statement of intent. The people who choose cryonics want to preserve whatever might be preserved until better tools exist. If revival never arrives, the attempt changes nothing about the person's end. If revival does arrive, the person wakes in a time they could not otherwise reach. In that narrow, personal sense, cryonics acts like one-way travel to the future by waiting. Subjective time between suspension and revival is near zero. Measured on the outside, the gap could be decades or centuries. One day, you lie down in a clinic. The next moment, as you would feel it, you open your eyes in a different era. Cryonics also sharpens how we talk about information in the brain. If identity rests in patterns of connections and strengths, what neuroscientists call synapses, then the central question becomes whether those patterns can be preserved well enough at low temperature to be meaningful later. Some researchers study connectomics, the mapping of those links at high resolution, to see what it would take to keep that information intact. Others argue that chemistry and dynamic activity are as important as wiring, which makes the target harder to hit. For now, the field does not have a common standard for saying how much of a person's mind is preserved by current methods. Storage itself is simple in one sense and fragile in another. Liquid nitrogen does not need pumps or compressors once the tanks are filled. It boils off slowly, and attendants top it up. That makes long-term cooling possible with basic infrastructure. Yet the chain of care must not break. A storm, a war, or a financial collapse could put the vessels at risk. Organizations keep backups, spread sites across regions, and set up funds to cover costs, but guarantees are not possible. The plan depends on generations of people continuing to tend to sleeping patients whose voices cannot call for help. Even if all the technical and practical challenges were solved, a revived person would face a world that moved on without them. Languages drift, laws change, friends and family may be gone. The social side of waking far ahead is as real as the medical side. This is not an argument against the attempt. It is part of the picture. Any serious plan would need counseling, education, and a path to belonging. Those questions are part of why cryonics attracts both interest and caution. Compared with ideas like white holes or engineered wormholes, cryonics does not ask the universe to provide exotic geometry. It asks human beings to hold a patient safe at very low temperature for a long time and trusts that future science will find a way back. No equations are broken. No speed limits are ignored. It is, in that way, a conservative approach framed in extreme patience. White holes, if they exist, would express the most dramatic side of curved space-time, pushing matter and light outward and perhaps connecting to distant places and times through a bridge. They remain unobserved and uncertain. Cryonics sits at the other end of the scale, rooted in clinics and steel tanks, seeking to pause biology and let history flow by. Both aim at the same practical result: to step out of one date and into another far ahead. One leans on the geometry of the cosmos, the other leans on cold and careful storage. Neither offers an easy return, and neither is ready as a travel plan today. Between those poles, the everyday facts still hold. Gravity shapes time. Speed shapes time. Clocks above mountains tick a bit faster than clocks at the shore. Orbits must be corrected for both motion and height. These tested pieces give the firm ground on which wilder proposals rest. If a tunnel through space-time ever becomes more than a diagram, it will still have to match those basic checks when clocks meet again. If a frozen patient ever opens their eyes, their first breath will still be counted by chemistry that obeys the same rules. Reaching forward in time by speed or gravity already fits cleanly with what we know, but turning the clock backward asks for stranger paths. Popular stories make the jump feel simple, like setting a dial and hitting a target year, yet real physics looks for routes where space and time themselves supply the path. The wish behind the DeLorean scene: hit a number, feel a jolt, and land in a different year, captures a human hope more than a method. In the lab, there is no magic speed that flips time. Speed slows your time relative to others. It does not let you rewind. To even talk about going back, you need geometry that lets a path loop in time as well as space. General relativity is where such loops first appear, not as props, but as solutions to the same equations that describe orbits and light bending. A wormhole is the standard doorway in these ideas. In plain terms, a wormhole is a tunnel linking two places in space-time. Picture a large sheet with two distant points on it. If you slide the points together and connect them with a short tube, a traveler could cross by going through the tube instead of along the surface. That picture ignores many details, yet it holds the key. A traveler would not cross the usual distance. They would use a shortcut written into the shape of space-time. If time is part of the shape, the shortcut could, in principle, link different moments as well as different places. Stories like Interstellar borrow pieces of this. The water world near the black hole shows how gravity can separate time rates. Later, the film imagines a space where many moments exist side by side and can be reached at once. That second step is fiction, yet it gestures toward a real idea, a closed, time-like curve. Time-like means a path, a person, or a clock could follow without breaking any rule about faster-than-light travel. Closed means the path returns to its own past. If such a loop exists, an event can influence itself in a way that stays consistent with the laws. Nothing jumps outside physics. The oddness comes from the loop, not from broken rules. A wormhole can be turned into such a loop if the two mouths age at different rates. One mouth might sit near a strong gravitational field or go on a high-speed trip and come back. Because time can pass more slowly along that path, the two mouths can end up out of sync. If, after that, the tunnel still connects them, stepping into the older mouth and out of the younger mouth is like stepping into an earlier time. Going the other way moves you into a later time. The limits are strict. You cannot go back to a date before the wormhole was made. The loop forms only after the time shift between the mouths exists. If you built the device today, the earliest you could visit would be today, not last year. There are famous puzzles here. If you can visit the past, what stops you from changing a course that led to your own trip? A simple version uses a pool ball rolling toward a wormhole. The ball enters, exits in the past, and bumps itself just enough to change the aim. Will it still enter? If it misses, the bump never happens. If it enters, the bump must happen. This looks like a deadlock until you notice softer outcomes. There are paths where the older ball nudges the younger one by a small angle so that both facts hold. The ball enters and the bump occurs. In those paths, the loop is self-consistent. This is the spirit of a rule some physicists use when they study such systems. Events that happen on a loop must fit together without contradiction. No scene is allowed that kills the conditions that made the scene happen. That rule does not prove that loops exist in nature. It only shows that, if they did, logic would not explode at once. The loop runs on tight bookkeeping. Keeping a wormhole open is the first practical war. Ordinary matter makes gravity that pulls inward. A tunnel made only of normal matter pinches shut. To brace it open, the equations ask for matter or fields with negative effective energy density. Negative here means the gravity they make pushes outward, the opposite of what we see with normal mass. Tiny, brief pockets of such energy can appear in special quantum setups. The Casimir effect, seen between two very close metal plates, is one case where the energy between the plates is lower than outside. That is a hint, not a building block. The sizes are minute, and the effect is local and short-lived. To build a human-scale tunnel, you would need a lot of negative energy, shaped and held steady. No one knows how to do that. The second wall is stability. A traversable wormhole would sit in a sea of radiation and particles. Light that feeds into the mouth can get blue shifted, which means each photon grows in energy as it rides the curved path. Even a trickle can, in theory, build into a flood near the throat. Calculations in semi-classical gravity, which treat space-time as smooth but include quantum fields, often find that the stress from those fields explodes as a loop in time is about to form. Stephen Hawking argued that this acts like a guardrail for cause and effect, a chronology protection that keeps loops from opening by using quantum back reaction to wreck the device just in time. This is not a proved law. It is a strong hint that nature resists time machines, and that any try will stir up the very effects that kill it. There are other paths in the literature, each with its own hurdle. A rotating black hole, described by a Kerr solution, has a ring-shaped singular core in the ideal math, and admits paths that swing around and return to earlier times. Add a speck of real-world noise, and the interior is expected to turn chaotic and block safe passage. An infinite spinning cylinder, the Tipler cylinder, can, on paper, drag space-time around so hard that loops form, but it must be infinitely long or spin with stresses beyond any known material. A universe that rotates as a whole, a girdle universe, allows loops everywhere. But our sky does not show the swirl patterns or global rotation that such a cosmos would imprint. Two long, thin, cosmic strings that rush past each other could, in theory, make a loop if they move fast enough and pass close. Stable strings of the right kind have not been seen, and the needed speeds press hard on limits that other parts of physics set. Each case is a study in how far the math can be stretched before other facts push back. Even if a wormhole could be engineered, the control problem is large. You would need to choose where the mouths sit, how they move, and how much time shift you build in. You would need to protect the throat from stray particles and fields that could trigger a collapse. You would need to plan for tidal forces, which are differences in gravity across your body or your ship, and keep those small enough not to harm. Communication between mouths would be tricky. Signals that try to cross the boundary can pile up or bounce. Some designs try to prevent signals from outrunning the boundary to keep cores under control. Navigation would demand a full map of the geometry, not a simple star chart. Paradoxes do not vanish just because a loop is consistent in one case. Questions about information remain. Suppose a traveler leaves a note with a formula that has no other source. The note is passed in a loop from older self to younger self, and then back again. Where did the information really come from? This is sometimes called a bootstrap loop. The loop can be self-consistent, but it feels odd because the note exists without a clear origin. Some physicists accept such loops as allowed if they are consistent. Others look to quantum mechanics for relief. One line of thought says that any attempt to change the past pushes the outcome into a different branch of events, so the past you knew remains untouched, while a new line of history unfolds that avoids contradiction at the price of multiplying outcomes. Another line keeps a single history and enforces that all actions on a loop must close without conflict. Both views are hypotheses. We do not have experiments that force a choice. Quantum rules also put limits on negative energy. There are quantum inequalities that say you cannot have large negative energy for long times without paying it back with positive energy. These bounds make it hard to collect the kind of sustained negative energy a macroscopic wormhole seems to need. Newer theoretical work has found clever ways to make small wormholes traversable in simplified models by letting two regions interact in a special way. But these setups live in toy versions of the universe that do not match our own. They are important for ideas, not for engineering. They show that, in principle, quantum effects can be tuned to let a signal pass where none could before. Turning that into a doorway for people is a different task. Popular films sometimes mix these ideas in helpful ways. The scene where a traveler can see many moments in one room at once suggests a block view of time. Past and future exist in the same four-dimensional structure, and the traveler is finding a path through that structure that most of us cannot access. That picture aligns with the fact that relativity does not mark a universal now. The film also uses a loop, where a future action sets up a past event that was always part of the story. This is one way to avoid paradox. The loop is not a change, it is how the event always happened. In such a story, freedom feels narrow, yet the laws stay intact. A question often raised is why, if time travel to the past were possible, we do not see travelers arriving all the time. There are many replies, some simple and some careful. The simplest is that it may not be possible. Full stop. Another is that any working device would be rare, fragile, guarded, or dangerous to use. A third is the creation limit. You cannot visit times before the first working device existed, so there is no way to drop in on ancient history unless a very old machine has been open all along. None of these answers prove anything. They show how a lack of visitors does not, by itself, close the case. It helps to return to scales. Time dilation by speed and gravity is measured today and used in clocks and navigation. Wormholes and loops are solutions in the math that need special materials and careful protection against quantum blowback. Rotating universe and spinning cylinder models teach us about how rotation drags space-time, yet they do not match the world we see. Cosmic strings, if they exist, are not yet found and may not have the right properties. A rotating black hole is real, but its interior is likely too unstable for safe paths. At every turn, the same pattern appears. The equations are generous, but nature sets hard conditions on what those equations can build. None of this means that looking is pointless. Work on wormholes has sharpened our view of energy conditions, the rules that say how matter and energy can curve space-time. It has led to new checks on how quantum fields behave in curved backgrounds. It has inspired better clocks and timing tests, because any real triator device would need exquisite control and measurement. It has also clarified language. When we say time machine, in a careful way, we mean a setup that creates a region where a time-like path returns to its own past and stays consistent. That tight phrasing keeps the dream inside the rules of known physics long enough to see where the walls stand. The most grounded path toward any kind of backward step still runs through wormholes, because they offer a way to trade long distances and long times for a short crossing. To make that path, you would need negative energy to hold a throat open, a way to shift the ages of the mouths, shielding and control to keep the throat stable, and a plan for managing signals so that cause does not trip over effect. You would also need an answer for the quantum stress that seems to rise as a loop is about to form. None of these pieces is in hand. A softer aim is to study self-consistent loops in simple systems, where you can check whether laws like energy conservation still hold on a loop. Thought experiments with billiard balls and light pulses show that many loops pick stable, self-adjusted paths that avoid contradiction. This is not a fix for human travel. It is a way to learn how a law-bound universe might behave if loops could occur. Sometimes, the result is that small changes in setup lead to large changes in the loop's outcome, a kind of sensitivity that would make control difficult. Sometimes, the result is that only a narrow set of starting conditions produce any loop at all. When people ask whether the past can be reached, the honest path is to separate what the math allows from what the world seems to allow. The math of general relativity leaves room for shortcuts and loops when you feed in the right ingredients. The world so far provides gravity that pulls, matter that is not exotic, and quantum rules that push back on large-scale negative energy. The gap between those two lists is where research lives. Kip Thorne and others have mapped that gap, showing how a controlled wormhole could, on paper, be turned into a time device by moving one mouth fast or placing it near strong gravity, then reconnecting it with its partner. Every step in that plan is a test, not a promise. Engineers would need to handle energies and fields far beyond anything now in reach. Physicists would need to show that quantum effects do not slam the door the moment a loop tries to form. Until then, backward travel remains a topic where clean equations meet hard limits, and where each careful model teaches more about what space-time demands from any path that tries to bend cause and effect into a circle. If a traversable wormhole asks for materials and control we do not have, the equations still leave another door ajar, a closed time-like curve, or CTC. Time-like means a path that a real object or person could follow without breaking the speed of light rule. Closed means the path loops back on itself. Follow such a curve and you would keep moving forward along your own time. Your heart still beats in order. Your clock still ticks in order. Yet the path could carry you to an event that, on the usual calendar, is earlier than where you started. Nothing jumps outside the laws. The loop is written into the shape of space-time itself. The idea entered physics in a serious way through a model found by Kurt Gödel in the 1940 seconds. He wrote down a solution to Einstein's equations in which the whole universe rotates. In that rotating world, the drag of space-time is strong enough to tilt the light cones the local limits on where signals can go so far that some time-like paths circle back. A traveler could, in principle, ride such a path and return to a point in their own past. Gödel's model does not match our universe. We do not see global rotation in the sky, and the pattern of galaxies does not fit that world. Even so, the model proved a point. The equations do not forbid time loops in every case. With enough curvature arranged the right way, a loop can appear. Other exact solutions hint at similar behavior. A rotating black hole, called a Kerr black hole, drags space-time around it. In the simplest math, very near its center there are regions where time-like loops show up. That is not an invitation to visit. Real black holes are messy, full of infalling matter and radiation, and small disturbances can destroy the neat inner structure shown in the math. A long, rapidly spinning cylinder with the right density, sometimes called a Tipler cylinder, can also twist space-time so hard that loops show up, but it would need to be unrealistically long or strong. Two hypothetical objects, called cosmic strings, if they passed by each other at high speeds and very close together, could also make a region with CTCs. Stable, long strings with those properties have not been seen. Each case teaches the same lesson. Loops are allowed by the rules if space-time is curved in extreme ways, but nature does not hand us easy setups. A CTC is not a corridor you step into like a hallway. It is a path built into the geometry. If you enter a region that contains such paths, you would not feel time reverse. Your own time always advances. What changes is the global bookkeeping when your path is compared with distant clocks. You could leave point A, follow the loop, and arrive at A's past. That picture also shows why loops raise so many puzzles. If you can arrive in the past, can you change what happens there? If you prevent the very trip you took, you break the loop that carried you. If you leave a note that has no author besides the loop itself, where did the information come from? Physics has two main ways to handle those puzzles without throwing out the loops. One is the self-consistency idea. On any closed time-like curve, events must fit together in a way that does not contradict itself. This view is sometimes called the Novikov principle. In simple models, it works. Imagine a billiard ball rolling toward a wormhole mouth. If it enters, it exits in the past and can bump its younger self. Some initial aims lead to contradiction, but there is always a family of angles where the older ball nudges the younger ball just enough that the younger ball enters and the loop closes neatly. No paradox appears because the outcome adjusts itself to a self-consistent value. The other way draws on quantum mechanics. In the many worlds view, any action that would clash with your own history simply pushes the result into a different branch of events. You can visit a past, but not the past that produced you. Your timeline stays intact. You influence a sister timeline. These are careful responses not proofs that loops exist. They show that if a loop formed, logic need not explode. They also show the limits. In the self-consistency view, freedom narrows. Only those actions that keep the loop whole are possible. You cannot do anything that blocks the cause of your own trip. In the many worlds view, you can act freely, but you do not change your own past. You create or join a different line of history. In both views, travel to the past loses the simple promise people often want. You can participate in events, but you cannot rewrite the path that brought you there. Quantum theory adds another layer to the story. In quantum field theory, a particle and its antiparticle are two sides of the same math. In Feynman diagrams, which are sketches that track interactions, a positron, the antimatter partner of the electron, can be treated as an electron moving backward in time. This is a bookkeeping trick that makes calculations work well, not literal human-scale time travel. It tells us that the deep rules do not panic when you flip the time label on a line. The math remains consistent. Quantum tunneling offers a second example. Particles prepared on one side of a barrier sometimes appear on the other side even when they do not have enough energy to climb over it. They have a small chance to tunnel through. To us, this can look like a cheat on distance or time. It is not a way to send a message to the past. The wave that tells the odds leaks through the barrier, and the peak of a wave packet can shift in ways that mimic superfast motion. No usable signal outruns light, and no cause arrives after its effect. Quantum effects do suggest that negative energy can exist in small, brief amounts. Between two metal plates held very close together, the set of allowed quantum vibrations is reduced, and the energy in the gap drops a bit below the outside value. This is the Casimir effect. That drop acts like negative energy density. It is tiny and local, and lasts only while the plates are in place. It is a clue that the ingredients needed for exotic spacetimes are not pure fantasy, but it does not give us the bulk, shape, and stability a macroscopic loop or wormhole would need. Paradoxes sit at the center of the human worry about past travel. The grandfather paradox is the classic case. If you prevent the meeting that led to your birth, who took the trip? The self-consistency answer says, you will not be able to take the step that blocks your own origin. Something will slip. A door jams. A word sticks in your throat. A coincidence pulls the meeting back on track. The many worlds answer says you can block the meeting, but the cost is that you slide into a branch where you were never born. Your home branch remains unchanged. Neither answer lets you both act and keep your original past. Each saves cause and effect in a different way. The bootstrap paradox is stranger. It asks whether an object or a piece of information can exist in a closed loop without an outside origin. You carry a music score back, hand it to the composer as a teenager, and the famous work is copied from your copy. The loop contains the score, but there is no first composer inside the loop. The cause and effect feed each other. Physics does not have a law that bans such a loop by itself. Energy can be conserved around the loop. The equations can be satisfied. What feels wrong is the missing source. Some researchers accept that such loops, while odd, would be allowed if a CTC exists. Others suspect that quantum rules or deeper constraints on information would prevent this kind of self-creation. That debate is open because we cannot test it yet. The predestination paradox is a tighter knot. You try to prevent an event and, in doing so, you produce it. The act you hoped would save the day is the cause that makes the day unfold as you were told. Stories use this often because it delivers a clean loop. A warning sent back produces the fear that leads to the very choice that triggers the crisis. A rescuer's attempt to pull someone away causes the accident in a different way. In a self-consistent world with a CTC, such loops are the ones that survive. In a many worlds picture, such loops are not required, but they can still appear as one branch among many. CTCs raise a technical issue that goes beyond stories. When you build a region in which time-like loops are about to form, quantum fields living on that background can behave badly. As the loop is about to close, the energy stored in those fields can rise without bound in the math. The back reaction of that energy on the space-time could then grow strong enough to kick the geometry away from the loop just in time. Stephen Hawking called this chronology protection. The idea that the laws conspire to prevent the building of machine-made CTCs. This is not a settled theorem that covers every case, but many calculations point in the same direction. As you push toward a loop, quantum effects push back hard. There are also limits on negative energy called quantum inequalities. They say you cannot keep a large pocket of negative energy around for long without balancing it with positive energy nearby. These bounds make it difficult to support the kind of long-lived, large-scale exotic matter a stable time device seems to demand. Even in models where a tiny wormhole is made traversable for brief moments by feeding in special quantum correlations, what passes through is usually a small signal, not a person or a ship. Those models teach us how quantum information and curved space-time interact. They do not hand us a portal. It helps to keep scale in mind. Quantum tricks work cleanly for single particles or small systems, and even they're only for short times. As you add atoms and warm the system, environmental noise destroys the fragile states that allow unusual behavior. This process is called decoherence. A person is made of astronomical numbers of atoms, warm and wet and always in contact with surroundings. The same world that lets us breathe and think is the world that wipes away the delicate quantum phases that tiny systems use. That is why quantum oddities do not jump to human size on their own. When people ask whether CTCs could ever be real, the balanced answer is that general relativity allows them in some exact solutions, but our universe does not show the global features those solutions need, and our best understanding of quantum fields hints at strong barriers against creating loops in the lab. Rotating universe models conflict with observations. Ideal interiors of rotating black holes are likely wrecked by infalling matter and instability. Infinite cylinders and perfect cosmic strings are not part of ordinary astrophysics. Even if geometry allowed a loop somewhere, reaching it and returning in one piece would be another challenge entirely. Yet the study of CTCs has not been wasted effort. It sharpened how we talk about cause and effect in relativity. It clarified what self-consistent means on a loop. It pushed research on how quantum fields respond to strong curvature, and it helped define the limits on negative energy. It motivated careful thought experiments that test whether conservation laws hold when paths circle back. In those models, energy and momentum can be tracked around the loop and kept balanced. The math does not collapse just because the path is unusual. Popular films give us fast routes into these ideas. Scenes where someone watches many moments of a room at once echo the block universe view, where all events exist in a four-dimensional structure, and now depends on your motion and location. Stories where a character discovers that their past self was guided by their own future action are examples of self-consistent loops. Other stories use branching timelines to keep both freedom and cause and effect intact. None of these stories proves anything about nature, but they are useful frames. They remind us to separate three questions: what the equations allow, in principle, what nature actually builds, and what human engineering could ever reach. Paradoxes keep us honest across all of this. The grandfather paradox shows the pressure on free choice if a loop exists. The bootstrap paradox shows the pressure on our sense of origin and authorship. The predestination paradox shows how an attempt to change a result can become the cause of it. The many worlds idea keeps freedom by moving consequences into a different branch. The self-consistency idea keeps a single history by narrowing what can happen on the loop. A third line, chronology protection, suggests that the combined laws of gravity and quantum fields may prevent loops from forming at all in any realistic setting. Each path protects cause and effect in a different way, and each has costs. There is a simple check that ties the discussion back to steady ground. Any real device or natural region that claims to bend time must also pass every ordinary test when measured from outside. Clocks that travel and return must agree with known time dilation. Energy must be conserved. Signals must not create contradictions when tracked step by step. Light must still follow the local rules set by the geometry, and matter must still resist stresses within known limits. The more exotic the claim, the more tightly these basic checks bind it. CTCs, if they ever appear in the world rather than the page, would have to live inside those checks. Even if a closed time-like curve could be made or found, it would not be a simple tool. It would be a region with strict rules that limit action to keep consistency. It would be sensitive to small disturbances and surrounded by fields that react to any attempt to push it into paradox. It would require energy forms that we do not know how to sustain. It might redirect would-be changes into different branches or block them in subtle ways. The dream of going back to fix a mistake or to save someone in your own past runs into these walls again and again. None of this removes the strange beauty of the idea. A CTC is a loop where the fabric of space and time carries you to an event already recorded in the big four-dimensional map, then brings you home with your own clock still in order. It is a natural extension of the same geometry that bends light and slows time near mass. It is also a harsh test of how strongly the universe guards cause and effect. As we learn more about gravity and quantum rules together, we may find new hints about where loops are ruled out and where they might survive in some limited form. For now, they remain a clear, rigorous possibility in the math and a stubborn challenge in the world we can touch, always inviting careful thought about what past, future, and change truly mean when time itself is part of the landscape. Stacking ideas helps only if each piece keeps faith with physics, so the first piece has to be power. Any device that tries to bend time must work on space-time itself, not just on objects moving inside it, which means energies far beyond anything in today's grids. Nature shows where such energy lives. A rotating black hole, a Kerr black hole, is mass and angular momentum wrapped together. Rotating here means the whole keeps a spin. Kerr is the solution to Einstein's equations that describes it. Close by, the spin drags space-time around, a real effect called frame dragging. There is also a region outside the event horizon called the ergosphere, where nothing can stand still with respect to distant stars, because space-time itself is being stirred. In that region, paths behave in unusual ways, and energy can, in principle, be extracted from the hole's rotation. Two routes for extraction are often discussed. The Penrose process is a thought-out method where an object splits inside the ergosphere. One part falls in with negative energy as measured far away, while the other escapes with extra energy. In astrophysics, a more practical route is magnetic, if strong magnetic fields thread the hot plasma near the hole. The field lines can act like wires that tap the spin and carry energy outward. This is the idea behind the Blandford-Snarjek mechanism. Neither is a blueprint for a plant you could build today, yet both point to the same fact. A spinning hole stores rotational energy that can, under the right conditions, be drawn off. A careful plan would place a station in a safe orbit around such a hole, far outside the horizon and outside the worst tides, yet close enough to catch power from the swirling plasma and the threaded fields. Massive coils and beam lines would convert the fluctuating flux into steady energy. Radiation would be severe and variable, so shielding, fault tolerance, and distance would matter as much as raw capacity. Nothing here lessens the engineering difficulty. The purpose is to sketch a source that meets the scale of the job, because folding space-time asks for more than incremental power increases. Shaping that power into a geometry that permits time loops needs a second piece. General relativity says that mass energy sets curvature, and curvature guides motion, including the motion of clocks. If you want a region where time-like paths close back on themselves, you need sustained, directed curvature. The Tipler cylinder is the classic model used to illustrate this. In that model, a cylinder made of extremely dense matter spins nearly at light speed. The math shows that if the cylinder is infinitely long and the spin is high enough, closed time-like curves appear near it. Infinitely long cannot be built. Finite cylinders tend not to produce stable loops without help. That is a limit, not a dead end, because it motivates alternate shapes. A ring is the natural finite cousin of a cylinder. Picture a massive ring, thick in cross-section, spun up so that its mass currents produce strong frame dragging in the surrounding space. The ring is not a metaphor. It is a rotating mass distribution designed to twist space-time in a controlled volume. Multiple rings, stacked or nested, could tune the field like lenses tune light. Superconducting structures might carry circulating energy with low loss. Dense flywheels could store angular momentum. Circulating plasmas could add current where solid matter would tear apart. The materials would need strengths beyond current alloys and composites. Hypothetical defects in space-time called cosmic strings, extremely thin, extremely dense lines left from early universe physics, are sometimes suggested as building blocks because their gravity is intense and focused. None have been confirmed in the sky, and their properties remain theoretical, but the idea sets the bar for what tough enough means. Stresses beyond steel by factors that seem out of reach today. Even if such a ring or lattice of rings could be built and spun, geometry alone would not give a doorway. It would create a field where special paths might exist. A practical path needs a corridor that can be aimed and entered. Wormholes fill that role in the equations. An Einstein-Rosen bridge is the simplest wormhole that shows up when you extend the math of a non-rotating black hole, but it pinches off too quickly for travel. Traversable wormholes need support. The support shows up in the equations as negative energy density, stress energy, that curves space-time in the opposite way from normal matter. Negative does not mean less than nothing in a casual sense. It means the sign in the curvature source flips. Quantum theory allows negative energy in small, short-lived pockets. The Casimir effect, seen between two very closely spaced metal plates, is the standard example. Modes of the quantum fields are squeezed out between the plates, lowering the energy there compared with outside. The measured force is tiny, yet it is a real tabletop sign that the sign of energy density can be reversed under special conditions. Scaling that effect from a lab gap to a wormhole throat is the core challenge. The throat must be kept open against collapse, kept smooth enough to avoid tearing travelers apart with tides, and kept quiet enough that incoming radiation does not build into a destructive storm at the boundary. The negative energy must be shaped like a collar around the throat and held steady for as long as a crossing lasts. Quantum inequalities constrain how large and how long negative energy can be sustained before the universe asks you to pay it back with a larger dose of positive energy nearby. Any realistic design would operate within those bounds, which is why the ring and its power matter. You would need enormous control to push the geometry toward the needed shape while staying inside what the quantum rules allow. A third piece is time offset. A wormhole by itself links two mouths that share a common now when they are first made. To turn the link into a time device, the mouths must age at different rates. One mouth could be parked deep near a strong gravitational field, where time runs more slowly, or sent on a high-speed journey and brought back. After this, the two mouths remain connected, yet their clocks disagree. Stepping into the older mouth and exiting the younger one amounts to a step into the past relative to where you started. Going the other way steps into the future. The maximum offset you can get is limited by how long and how extreme the offset process is, and by the fact that you cannot go back to a date earlier than the wormhole's creation. Threading these pieces together suggests a system with a rhythm. The Kerr hole provides rotational energy at scale. The station converts a stream of that energy into steady power. The ring lattice uses that power to generate controlled frame dragging in a clear volume. Negative energy fields are produced and shaped to support a small, traversable throat at the center. One mouth is carried through a preset path, either an excursion near strong gravity or a high-speed loop, and returned. The mouths are then held fixed relative to the ring, so the geometry around the exit stays quiet. The corridor opens for short windows when the quantum stress and external radiation are within safe limits. Each window would be brief and carefully scheduled because the nearer you push space-time toward a closed loop, the more quantum fields tend to respond with rising stress. Sensors tuned to those fields would decide when the window is safe and when it must close. Such a system could not operate without navigation that understands both place and time at high precision. On Earth, satellite navigation works because the system knows where each satellite is and how its clock drifts due to speed and height, and the receiver solves for its position by comparing arrival times. A time machine has a harder job. Across minutes, the planet rotates and moves along its orbit. Across hours, the sun's position changes in the sky. Across longer spans, Earth's axis slowly wobbles, the moon tugs, and the whole solar system moves around the galaxy. A small timing error could put a traveler outside the atmosphere. A position error could put a mouth inside rock. The reference frame must be tied to stable astronomical points and updated with all known motions. Quantum entanglement is a candidate for building stable references across long baselines. When two particles are prepared in an entangled state, measurements on one are correlated with measurements on the other in ways that do not fade with distance. Experiments led by Anton Zeilinger and colleagues demonstrated quantum teleportation and long-distance entanglement with photons over fiber and free space. Teams led by Jianwei Pan extended those ideas to satellites, showing that entanglement can be distributed from orbit to ground across thousands of kilometers. These systems do not send information faster than light. What they can do is provide shared, tamper-evident correlations that act like a common reference. A network of entangled pairs, refreshed over time and tied to well-known astronomical coordinates, could serve as anchors. A traveler could carry one member of an entangled pair and use it to check alignment with its partner stored at a known place and time. Classical signals would still be needed to complete any exchange of information, but the entangled correlations would check identity and timing in ways that resist drift and interference. A practical control stack would layer tools, Classical radio and laser beacons would provide course position and velocity. Pulsar timing, using the regular flashes from rapidly spinning neutron stars, could add an all-sky clock, because pulsars act like natural lighthouses. Optical clocks on the station and at ground sites would establish a timescale stable enough to see tiny gravitational shifts. Entangled links would bind these references together so that a disturbance at one node does not propagate misinformation to others without being noticed. All of this would feed the ring lattice and wormhole control systems, which would tune fields in real time to keep the throat centered and quiet. Hardware at the edge of a Kerr system would face environments harsher than any spacecraft has seen. The accretion flow around an active hole is hot, bright in X-rays, and full of shocks and magnetic reconnection. The ergosphere sits inside this storm. A safe orbit would sit well outside the horizon and outside the thickest flow, using long tethers, beamed power, or remote collectors to harvest energy and send it back to the main platform. Materials would need to shrug off radiation damage, charge buildup, and micrometeoroid hits. Active cooling would be required. Redundant pathways would handle sudden losses of input power. Safety interlocks would watch for growing quantum stress, rising fluxes of high-energy particles, or unexpected frame-dragging changes as the ring spins up, and would ramp the system down before a threshold is crossed. Inside the ring field, the main risks are tidal forces and blue-shifted radiation. Tides are differences in gravitational pull from one side of an object to the other. Strong tides can stretch or compress. The field must be shaped so the gradients in acceleration across a person or a small craft stay within human limits. Blue shift means that light coming toward the throat can gain energy as it falls into the region of strong gravity. Even a faint background can become dangerous if it is focused. Baffles, absorbers, and dynamic field shaping would be needed to keep the throat from becoming a lens that concentrates harm. Monitoring would be continuous, with the window for passage opening only when the environment is within set bounds. Negative energy production and shaping is the most speculative part. One path uses squeezed quantum states of light or matter, which let fluctuations dip below their usual values for brief times and in small regions. Another uses arrays of Casimir-like cavities, tuned and switched to create patterns of reduced energy density that add up where the throat needs support. Both would be limited by quantum inequalities, so the design would work with many small contributions that overlap in time rather than one large steady source. That, in turn, would make the passage windows short and would demand precise timing from the navigation and control stack. Even with all pieces in place, limits remain. Any time offset is bounded by how long one mouth can be kept on its offset path and by how stable the throat stays while the offset is built. Chronology protection may manifest as rising quantum stress that forces the corridor to close before a true loop forms. Energy costs scale quickly as you try to enlarge the throat or lengthen the safe window. The ring's spin must be kept below the point where the structure tears or radiates away energy faster than it can be supplied. Each subsystem is a gatekeeper. Power, materials, fields, quantum limits, and control. A careful reader will notice that each part of this stack, Kerr energy extraction, frame dragging rings, negative energy support, clock offset, and quantum anchored navigation, already lives inside known or seriously studied physics. None asks for a new law. Each asks for extreme versions of known effects and for levels of control far beyond current practice. This is exactly why stacking matters. No single trick is enough. Rotating holes provide scale. Engineered rotation shapes a working region. Quantum effects give the sign of energy needed to hold a passage open. Relativity provides the way to build a time offset. Precision, timing, and correlations provide a way to aim and verify. There is a temptation to ask for a single switch or number that makes the whole thing work. Physics refuses simple switches here. The system would behave less like a car and more like a laboratory the size of a small moon, run by clocks and sensors, edging up to thresholds and backing off when the universe pushes back. Each success would likely be small. A throat that stays open long enough to pass a pulse of light, then a tiny probe, then something larger. Each failure would teach which bound bit hardest: quantum inequalities, stability of the ring, energy capture, or navigation drift. Even as a thought exercise, folding these ideas together clarifies the roles. Rotating gravity supplies energy and a natural form of space-time twist. Engineered mass currents add local control. Quantum fields supply the sign change needed to make a corridor. Motion and gravity provide offset between mouths. Entangled networks, pulsars, and optical clocks give a map that cares about both place and time. None of these removes the hard limits seen in earlier discussions. They give a way to see how a device would have to respect those limits at every step while trying to trace a path where a time-like curve closes and returns to an earlier event. A design that stitches together rotating black holes, frame-dragging rings, negative energy corridors, and quantum-anchored navigation reads like a plan drawn on the edge of what our laws allow. Each part is rooted in physics we can write down, yet each part also leans on extremes that push against known limits. A Kerr black hole can store vast rotational energy, but building and protecting a station close enough to tap it would test every material and control system we can imagine. A spinning ring can shape space-time locally, but keeping it intact at the needed speeds demands strengths far beyond current matter. Traversable wormholes require negative energy arranged with precision, while quantum inequalities restrict how much and how long that negative energy can exist. Entangled networks can give shared references, yet they do not move messages faster than light, so any navigation system must still respect causality and noise. When these pieces are placed side by side, the gaps are clear. The blueprint is coherent on paper, but it waits on breakthroughs in materials, energy handling, quantum control, and stability. The theories do not slam the door. General relativity admits geometries with shortcuts and loops. Quantum theory allows brief pockets of negative energy and correlations that bind distant systems. Precision timekeeping proves that rates of time do change with speed and height, and technology already uses those changes to keep navigation working. These steady facts leave a narrow corridor between forbidden and possible with great difficulty. That corridor is where careful imagination lives. It is also where engineering reality sets hard conditions. Before any human steps through a corridor in time, smaller goals would come first, sustaining a tiny, traversable throat long enough to send a light pulse, measuring how quantum fields stress the boundary as controls vary, shaping a local frame-dragging field without tearing the machine that produces it, verifying that clocks brought together after complex paths agree with predictions within their tiny margins. The most likely path to genuine time travel, in the strict sense of moving to a different date, still points toward the future rather than the past. We already see futureward steps when motion or gravity slows a clock. Astronauts return a hair younger than they would be had they stayed on Earth. Satellites run fast or slow depending on orbit and altitude, and we adjust them. These are small but real changes that match the rules precisely. Pushing them to dramatic scales would require speeds close to light or fields close to compact objects. and those carry risks we do not yet know how to manage for humans. Yet they are not dreams outside the laws. They are extensions of effects we measure every day. Backward travel remains the hard case. Wormholes and closed time-like curves exist in exact solutions, but they appear alongside demands the world seems reluctant to meet. Exotic matter in stable bulk, infinite or near-infinite structures, or environments that turn unstable when even tiny disturbances are included. Quantum back reaction often rises as a loop is about to form, hinting that chronology protection may be more than a clever phrase. Even if a loop could be created, self-consistency would narrow actions until change becomes participation rather than revision, or branching views would move consequences into a different history, leaving your own untouched. These outcomes do not kill curiosity. They define the terrain on which curiosity must walk. A full program aimed at time control would likely deliver returns long before any machine opens a door. Pushing optical clocks to better stability makes gravity visible at centimeter scales and improves navigation, surveying, and Earth science. Studying strong gravity near black holes refines our models of jets, accretion, and high-energy radiation, which in turn tells us how galaxies grow. Exploring negative energy phenomena in quantum systems sharpens our understanding of field theory and may lead to new sensors or communication security techniques. Efforts to simulate curved space-time in laboratory analog gravity systems using superfluids, optical media, or metamaterials build platforms where ideas can be tested safely at small scale. Each step is valuable on its own. None requires a promise that a time device will follow. There is also a human layer that any serious design must face. A time corridor that works even for tiny objects would raise questions about safety, rights, and responsibility across events that no longer have a single order for all observers. Navigation errors would not be simple mishaps. They could strand travelers far from help in both space and time. Record-keeping would need rules that define what counts as a reliable history when paths reconnect. Security would need to consider how information on loops is handled and whether closed chains of data can be trusted. These concerns are not reasons to stop thinking. They are reminders that technology at this scale would change more than transportation. It would touch how societies understand records, law, and memory. The most grounded statement we can make is modest and firm. Physics, as we understand it today, permits time to pass at different rates for different paths, and our tools are sensitive enough to use that fact. The same physics leaves narrow openings for shortcuts and loops under extreme, tightly controlled conditions. The openings are balanced by strong counterpressures, stability requirements, energy bounds, quantum limits, and the tendency of small disturbances to grow violent in the very regimes where a shortcut would be most useful. That balance explains why we do not see travelers stepping out of thin air, and why laboratories pursue precision clocks and gravity measurements rather than machines that promise to erase yesterday. None of this drains the subject of meaning. Asking whether time can bend pushes us to refine our best theories where they meet. It gives us clean targets, better clocks, better measurements near strong gravity, better control of quantum states under stress, better maps that combine place and time. It keeps attention on the joint frontier where general relativity and quantum theory must someday be united into a single, tested framework. If that union comes, it may redraw some lines, it may place new limits, or open small, safe regions we cannot yet see. Either outcome would count as progress, because both would convert speculation into knowledge. If a later civilization learns to harvest energy from compact objects, to to shape large-scale curvature without collapse, and to arrange quantum fields in stable, useful patterns. Then doors that now look sealed could open a crack. Those are high bars. They may stay high. The absence of visitors and the quiet of the sky suggest that either the bars are beyond reach or the costs and risks outweigh the gains. But the absence is not proof. It is a boundary condition on our models and a nudge toward careful humility. A clear way to finish is to bring the story back to what we can touch. Clocks on mountains tick a little faster than clocks by the sea. Spacecraft adjust for speed and height to keep time aligned. Light bends near mass, and signals stretch as they climb. These are the daily footprints of a universe where time is part of the landscape, shaped by motion and gravity. From those footprints, we build instruments, tests, and, for now, dreams that stay close to the laws. If someday those laws guide hands steady enough to hold a corridor open, the first proof will not be a grand leap. It will be a small signal that leaves, returns, and matches a prediction to the last decimal, showing that a path through space-time can be shaped as planned. Until then, asking careful questions about time remains one of the quiet ways we make sense of a strange, patient universe.